Welcome to everybody's favorite new series, Test Gear Tuesday. That's right, it's been a while. I know you've been hungering for a new episode, and moreover, more frequency counter stuff. So I oblige you. Here we are with a frequency counter stuff. Today we're going to look at this Victor VC3165 frequency counter. This frequency counter covers from 0.01 hertz all the way up to 2.4 gigahertz. I put this frequency counter through its paces. Now I will not bore you with all the on-screen testing, although I could if you so desire. Go ahead and tell me right now, and I'll change this video just for you. I'm waiting. But for everybody else who is not willing to wait, let's carry on, shall we? This frequency counter sports two BNC connectors. BNC channel number A actually has two modes, a mode 1 and a mode 2. No emojis available on this counter, unfortunately, if you're into that thing. Mode 1 goes all the way, actually let me do this in reverse order because that's how they are. Mode 3 and mode 2 is on this port, mode 1 is here. So mode 3 covers 0.01 hertz all the way up to 2 megahertz, and then mode 2 goes all the way from 2 megahertz all the way up to 50 megahertz. Over here on channel B, mode 1 covers 50 megahertz all the way to 2.4 gigahertz. Here we have a manually selected rotatable gate time, and I just dropped my pointer. I hate when that happens. It is a big pointer, and I would hate for somebody to bump into it, trip over it, like I just bumped into the camera trying to get my pointer picked up off the ground. So that is that doodad right there. This doodad right here is a button. Matter of fact, all these doodads are buttons. That's not important, but what's important is what they do. And this one here is AC/DC because it likes the rock band AC/DC. Nay, it don't go AC/DC, but it listens to AC/DC. Actually, on this device, AC/DC is for coupling. Now, we will not be DC coupling, we will only be AC coupling. If you get DC coupling, then you have to go to your doctor and get a shot and get that cleared up. Don't want that. This button right here is our attenuator, X1, X20. And this one here is our function to navigate between the modes and the ports here. This here is our period button. And that's the fact jack period. That's a hard period. I've really not played with period, so I don't know if it's accurate. I'm sure it's fairly close because for the most part the frequency counter is fairly close. And then we have a reset button, so if the device locks up on you, you just mash said button and then it'll reset the device into a status of first powered on. Now, some of you may remember a frequency counter I reviewed not too long ago in a previous video, which only makes sense. I'm dumb for saying things like that. But then again, what do you expect for the money you're paying for this show right now? I gotta tell you something. This is not going as planned, but this is a lot better than the first take. I spent an hour doing the first video, got so frustrated I just stopped. It was not going too well, so I hope for your sake this video goes a lot smoother. Okay, very well. Rented lips, hold on. Where were we? There we go, those were my words, Jack. Now, in my previous video with the sinometer, sonopometer, whatever you pronounce it, VC2000, in that video I declared how much I really hated certain aspects of the frequency counter. Well, I have to say that disdain travels forth with this frequency counter. This frequency counter has those same earmarks that I did not like in that with that frequency counter. And what I don't like about it, for those that did not watch that video, is simply the display here. The display is washed out with direct lighting. Right now it looks pretty good because I had to manipulate my lighting to ensure it wasn't washed out, and my camera angle. Also, a lot of glare. So with your direct lighting, you're going to run into the joys and pains of that. Also with the lighting, if the lighting is normal or intense, this display washes out real quick. In my previous video, I talked about the thought of just swapping out those digits to a red color. That's not a problem. That very well can happen. However, this filter is a green filter as well as the display, as the digits. So you may get some kind of trippy 1970s acid kind of reflux kind of look on the screen. I don't know. Or you just whack that out and put a new one in. Your choice. The other thing I don't like about this frequency counter, or frequency counters like this in general, because it's not specific to this one, it's a lot of test gear and other devices. I do not like the fact that the hard switch is in the rear. There's no other way of powering this device on or off. It is with that hard switch in the rear, or you put it on a power switch, a power strip, and control it that way, which to me is a big waste. I also don't like about this is that it is very light. If it's on something that is slippery, it will slide all about. Now, most of you know that I use a standard cotton towel on my workbench. I say most of you because I've had actually several people write in and ask about issues with my carpet and static electricity. So let me just debunk that. This is a cotton towel. And as you saw, it does slide all over the place fairly easy. And if you put this on a hard surface, same thing. So you would probably want to put some rubber stops on here to help with that, or a heavy weight, or nail it down to the workbench. Losing focus here. Let's see, what else do I want to not tell you about this frequency counter? Well, I think that's really about it. Now, as far as sensitivity from 100 hertz all the way up to 50 megahertz, they're calling for less than 120 millivolts RMS, and then for 50 megahertz to 2.4 gigahertz, it's calling for 50 millivolts RMS all the way up to 300 volts RMS. And I will tell you, in my testing, that is fairly accurate. I found that this is at most 600 millivolts to input a signal, and at minimum was only 7 millivolts. So that's really, really good. Now, as far as sensitivity is concerned, my Cenometer VC2000, which I no longer own, I had given that away to a fellow YouTuber, Don. I'm a junk collector, and you should check out his channel, subscribe, tell him I sent you, he'd thank you, and then he'd flip me $100 bill. So it's well worth it to me if you sub to him. Just kidding, of course. It's actually 25. Forgot what I was saying. Just got to rewind the tape to figure out what I was just saying there. Oh, sensitivity. The Cenometer actually was a lot more sensitive than this. A lot more. Keep that in mind. Now, I have not opened this device. I don't know what it looks like. I've watched all the YouTube videos on it, and I have seen a few pictures on the interwebs, and I do know that this does use the very same prescaler, which is a MB506. Same specs. However, with this one here, I find that it actually performed a little better. Now, as far as my testing is concerned, I use 2 RF signal generators. I use for the lower band, a BK Precision 4070 Alpha, and that goes from 0 hertz all the way up to 21.5 megahertz, and that is a multi-mode AM, FM, sideband, etc., etc. A Swiss Army knife of signal generators. And then for frequencies above 21.5 to 2.6 gigahertz, I use a lab grade HP 8660 C as in Charlie signal generator. I will not bore you with all the tests that I did. Now, testing environments, equipment, all that good stuff can change from one unit to the next. So what I find on mine may be different on yours. I'm sure you are well aware of that. At this point in time, my signal generators have been turned on and powered up for almost 12 hours. As stated, the lower frequency on this is 0.01 hertz. Even though I am capable of going that low on my B and K, I was unsuccessful at going that low on this device. The frequency that we're looking at right now is in fact the lowest I'm able to read on this device, and that frequency that we're looking at is 0.40 hertz. That's right, just about or just shy of half a hertz. The minimum value I am able to keep a steady signal is at 60 millivolts, and that is definitely in range. Range again is less than 120 millivolts, so we're definitely on top of things here. The lowest I was able to go on RF was actually 3 hertz at 190 millivolts, so significantly different than just on a sine wave. One other thing I'd like to notate on the gain control knob here, this is a rotatable control. There is no detent. There is nothing in the control that's going to give any form of feedback to let you know where you are. It's just a visual on this scale, and the gate time on that ranges from 100 milliseconds to its fastest and 10 seconds on its slowest. Right here we have its fastest at 100 milliseconds, and here we have its slowest at 10 seconds. And then at 1 kilohertz, I was able to clock this at minimum of 50 millivolts, and on sine wave and on RF, it was 100 millivolts. Now, when I do my testing, I try to ensure that the third digit is stable without dancing about. So even though you are able to get this to read lower, read lower on either less power or lower in frequency, the digits do dance and jumble about. As far as me, when I'm testing, my prerequisite is the third digit from the right of the decimal. As long as that holds steady, I'm good. I don't need anything really a lot further along in count. I'm not that precise. I don't do anything that requires that. So for me, third digit to the right, I'm fine with. And here I've inputted a 1 megahertz signal, and we're still on that. So let's go ahead and change to where we need to go. And for that one, we actually need to go to number 2. And so I went to function, and I changed where I needed to go, and then I hit confirm, and it brought us right back. And so for 1 megahertz, I found that 100 millivolts sine wave was a minimum, and 220 millivolts on RF. And now we're going to go to 5 megahertz. And 5 megahertz on sine wave was really, really surprising. This is where we made a big jump. At 5 megahertz, it only takes 9 millivolts to activate the frequency counter. On sine wave, on RF, it's 18 millivolts. What a big, big difference. On 10 megahertz, I find that it takes 13 millivolts on RF, on sine wave, and 25 millivolts on RF. And then on my highest frequency on this BK generator is 21.5 megahertz. And what I found on sine wave, it takes 32 millivolts to excite, and on RF it takes 51 millivolts to excite. Okay, so I've switched over to port B, and we are now connected to the Hewlett-Packard signal generator. The frequency coverage for this channel is 50 megahertz all the way to 2.4 gigahertz, and it's calling for a voltage range of 50 millivolts all the way up to 300 millivolts. And so let's go ahead and put this on 50 megahertz. And you see we do that splendidly. I find that for this, it only requires 33 millivolts on RF. And then we go to 100 megahertz. For 100 megahertz, I find that it only requires 15 millivolts. For 250 megahertz, it requires an astonishing 7. That's right, 7 millivolts to activate this. Really, really impressive. And then we go all the way up to 500 megahertz, and here it's 18 millivolts. Let's go to 600 megahertz. That takes 13 millivolts to excite it. We'll go to 1 gigahertz. 1 gigahertz, we jump up to 21 millivolts, and now we go to 1.5 gigahertz, and that calls for 39 millivolts. Let's go to 2.0 gigahertz, or 2 gigahertz, whatever you prefer. That doubles. Well, more than doubles. It goes all the way up to 74 millivolts. And then we'll punch in 2.5 gigahertz. And for 2.5 gigahertz, it requires 270 millivolts to excite. When we're over on channel A, number 3, we're not getting to 2.4 gigahertz. Why? Because it's out of our spectrum. If we go to number 2, we're not going to 2.5 gigahertz because it's out of our spectrum. However, if channel B was to break off and fall apart, no more, no mas, it's okay. You can live with that. Check this out, boys and girls. That's right, your lying eyes are not deceiving you. It really does go to 2.5 gigahertz. Channel A, when you're on 3. To show you real quickly that this is not a fluke. Now, even though this is not a fluke, and I'm going to show you, there are a few dead spots within the entire spectrum. I did not log them, but I'm going to spin my thumb wheel. The signal generator is at 226.7, which is what we're at here. I've repositioned the camera so we could see my signal generator, and I've killed the overhead light so we could see the display better and not so washed out. But I think you could see that, yes, we really are on 2.5 gigahertz, and that is what we're showing. I'm going to take my spinny wheel here. Throughout the entire spectrum in this configuration, there are some dead spots. I did not log the dead spots. This is not going to be a primary frequency counter for me, but just to show you that this really does function out of spec, and it's really impressive. So we'll spin the wheel of love. That's 2208, which is what we have, 2.208 gigahertz. 1968, this is what we have. Oh, you know what? Let's do this one. Here's a cool number. This number is awesome. If you don't like this number, you suck. There we go. Had to adjust my my power. But there you go, 1776. What an awesome number. Okay, so I'm a few hertz off. But hey, hertz don't it? What an awesome number. 1776. 1544. Let's speed this up, shall we? 800 megahertz. 500 megahertz. 345 megs. 408 megs on the generator. 412. 411. 410. 409. Okay, so I'll call it at get a little bit more moose juice. So we're at the verge. We're not stable. So let's go ahead and call it at 410 megahertz all the way up. So, no, I lied. So you can see that either way, the device is, we're at 415. The device is pretty awesome. Now, as far as on channel B is concerned, what I found was actually its limits. Now, this signal generator is rated only at 1 megs. However, what I found, of course, it goes out of range. I found that at 792 is about as low on that generator it'll go. On my B&K, I could actually go to 600 kilohertz. Of course, we need a little bit more power. We're up around 700 millivolts. On this frequency here, we need 680 millivolts to get here on the HP, and on the B&K to get to 600 kilohertz. We have to go all the way up to 1.7 volts, but it's stable and it can do it. Now you're saying, Jack, my man, what about the high end, brother? Say, man, what about the high end, fool? Well, let me tell you about the high end. The high end is there. We only go to 2.6 gigahertz on this counter, so we got to go 2.59999 gigahertz. And no, I was not speaking German. I was not saying no. Not unless you are German, and I need to say no to you. So there you go. 2.6 gigahertz. Is that awesome or what? I do want to say, I had to sit and ponder how I'm going to do these videos. We will not put this away just yet. We will see this in a future video, and we'll play with it just a little bit more. That's all I could say. I don't want to ruin it for you. I know how much you like surprises. Okay, so here we are at this point of showing you the device. A walk around tour. We've already looked at the front panel, side panel, nothing exciting. Back panel, That's where the fun's at, right? We have your EIO, what is it, the EIC plug, standard computer plug. And what's really cool about this one, it's fusible right there. Selectable mains input. And then there's that doggone hard switch I keep talking about, I know light. This side looks pretty much like the other side, except for, less yellow, less white, except for it's, yellow, you want yellow. There's your yellow. And then on the bottom, you see, all hard, no rubber. Got a pull-out handle, which you could lug it around with, or you can position it wherever you would like. All together now. Ooh, exciting. Let's get a tool. Let's crack it open. Let's check out our guts. A lot of people have complained about the craftsmanship on these devices, bad grounding, bad soldering, just poor craftsmanship. And so I just want to give this a quick once-over as well as show you. I know you can't see too much in this view here. We got ground right here that's on a spring, which is in return soldered down to the board. And then everything breaks apart here, and I'm going to break it apart in just a moment. Give you a once around. And here we have, see the inside of the back panel. And the back panel unfortunately does not break away. It's glued in. Now if you rip the head off, well, looks like we have a couple of ways to pull it off of the board. Now these devices use a 12 megahertz clock. Well, that one was being a pain to get out. We got a controller here. And then here is our RF ports. And you can see that's really, really not easy to get to. So even if you thought, well, I'll just pull this board out to access this one, I was thinking the same thing, except for it appears that this PC board, is overhanging a little. So I mean, you might be able to come out at an angle, and then it might come out. $10K pot. And then the guts here. Now, looking at this board and remembering what the last one was, I was thinking maybe this is going to be the same board, just a different head and configuration, but it's not. So over here is where the RF input used to be on the other one, and then it would go through this network. This is should be our prescaler, and I thought the prescaler was closer over here. I'd have to look at my reference photos again, refresh my brain. This part definitely is the same. Underneath here, this is our heater, and underneath there is going to be a 12 megahertz crystal, and then we're going to have should have a resistor going over it, and then a lot of thermal compound buried on top of it to keep it all nice and warm. And then you can see right here, this is our adjustment to calibrate the crystal. And so I know that kind of feeds in this away. Couldn't begin to tell you exactly, but something like that went through this. And so here is a little bit better view for you to see. Been watching way too much Davy Jones, because I almost come back and said, and for all you Transformer aficionados, there you go. But I won't. January 7th, 2000, number 7. Thank you very much for watching this episode of Test Gear Tuesday. We will meet you in the next one. Thanks for watching.